Hello and welcome to class 18 of my course on quantum physics 2. And here we are talking about the quantum mechanics, the application of quantum mechanics 2. We are now basically dealing with the quantum computation. I told you, there are two branches of quantum mechanics. One is the approach of Schrodinger, where you take up the wave function as a mathematical function. Another is the approach of Heisenberg, where you describe wave function as a state vector. Because the entire study of quantum computation depends on the mathematical basis is state vector. So what I tried to tell in every class before this is that what is the mathematical origin of the ideas of state vectors. So I define state vector in front of you, that it is a fundamentals are defined in front of you. These are some elements only, they have to satisfy some properties. And we have taken up always Cartesian system as an example of the state vectors. So with all these things in mind, actually moved up with the basics of the algebra of the state vector. Then I defined a term called basis vector. In Cartesian system, ijk's are the basis vectors. So it depends on the number of basis vector equal to the dimensionality of this space. And any point there, in Cartesian space, you define with that linear combination of basis vector, and they together defines an arbitrary vector, say R1 as you could see. Now the meaning of that point in this is a position, a point in the Hilbert in the position space. So after that, I move from 3-dimension to n-dimensional space, where a point is also defined by an arbitrary vector as a linear combination of the basis, but the coefficient may not be real. That space is called Hilbert space. And you know, our quantum bit is basically a point in 2-dimensional Hilbert space with basis zeros and ones. So you can express that any arbitrary quantum bit as a linear combination of the zeros and ones. So like alpha 0, beta 1, as you could see, where alpha is the coefficient, linear expansion, and beta is the alpha beta the coefficient, and zeros and ones the basis vector. And particularly last lecture I mentioned that the probability of finding the suppose an electron in hydrogen atom, it may be there is only one electron, and zero state may be the upspin state of the electron and one state may be downspin state of the electron. So probability of finding the particle or electron in one of the state is the modulus square of the coefficient. There is alpha square is for zero state, beta square is for one state, and total probability is 1. Now the idea is that so if I make one of them as 0, say alpha 0, then you convert your case to psi is equal to the 1 state, and so your quantum bit is a quantum mechanical state, but maybe spin up down state of the electron is a quantum bit. Similarly, if you make beta 0, then your psi becomes 0. That means, for example, the spin up state of the electron. So major difference with the classical computation is that here a spin state, the quantum mechanical state of the matter, in this case electron maybe, is defining a qubit. Another wonderful idea is that it is not just zeros and ones, they are mixtures. That is the beauty of quantum computation because of the superposition principle. If 0 is an allowed state, 1 is an allowed state, their mixed state is also an allowed state, okay? So their mixture is also an allowed state. And only thing you have to satisfy the total probability of mod alpha square plus mod beta square has to be 1. So the mixed state, like suppose alpha is 1 by root 2, beta is 1 by root 2, that is an allowed state, okay? So it is not just 1 and 0, their mixed states are also allowed state in quantum computation. So that is one of the advantage. Number of quantum bits are that's why enormously high, okay? Not just zeros and ones, their mixed states are also enormously high. You can see the picture, it's wonderfully changing. That's why I've kept that animation. 1 and 0 may be up and down spin state of the electron. But in between, if you change the coefficient of those alpha beta, so many new states are being generated, and you can see. And the final one is the mixed state. Okay, it is changing. Okay, the bigger picture actually, depending on the coefficient, you see it is changing. The spin vector is rotating. Spin state is the magnetic state. Today I will be highlighting that issue. So that is the beauty of the discussion, is that the number of quantum bits are enormously high. Only thing, you have to manipulate electron spin, and because mod alpha square plus beta square equal to 1 is the equation of a circle. So therefore, if I could define a circle, any point on that surface of the, on that point on the circle is a quantum bit, and in 3D you can imagine a as you can see there, it is, the picture is coming out there. If you define a sphere, we may call it a block sphere representation. Now, because alpha beta may not be real, alpha beta may be in general complex quantity. So to take care of the, if they are added with some phase part, so that's why to take care of all those things, we define a sphere, sphere. Now the beauty is that you see it is being traced out with that picture. Any point on that circle that is coming out is a quantum bit. A number of quantum bit, any point on the sphere, as a matter of fact, is a quantum bit, and it enormously high. Not just 1 and 0, many are there. This is called block sphere representation of quantum bits. Now after that, I have actually ended my previous discussion by telling how do you realize these quantum bits. Because it is not zeros and ones only, not just high and low only as you think in classical way, but their mixtures are also allowed state. But suppose if I compare with classical computation, there are 2 digits, binary digits are there, zeros and 1, which you realize them as high and low voltage values. But here, zeros and 1 may be the spin state of the electron, up and down spin state of the electron. So now what you have to do, it is not just zeros and 1, their mixtures are also allowed. So intermediate spin states we need to know, which should be representing the quantum bits. Okay. So that is an important issue. As just see the picture, okay, the formation of the, you see there are so many intermediate states are there. Okay, you can see not zeros and 1, up and down are shown there, but there are many combination of up and down. That means many linear combination of those up and down. They are all allowed state. Okay, and you can see depending how do you attain the state. I have tried to provide a glimpse of that. You see spin state is continuously changing, and those change state are at the actually excepting up down, whatever you get, these are all intermediate state. Okay, and you see something is changing outside, so something from external is must be there to control this thing, everything. So before knowing all these things, you need to know what is the electron spin properly. Okay, now the spin of the electron, you know, spin is basically one of the intrinsic property of the electron. Say if I say electron, actually 2 things comes to our mind. Say you see, look at the animations. Okay, first you see that, after that I will explain. You see electron is orbiting around. Electron orbiting around means electron is a charged particle. You know, every electron has got 2 states. One is a charged state, because every electron carries some amount of, every electron has got 2, if you have to define electron as a matter of fact, first is the charge of the electron, it's got some negative charge. So if it flows, negative charge flows, I get a current. So that is called electrical property of the electron. But at the same time, by Bohr-Savart law, as you studied in the magnetostatics courses, that if a charge flows and if a current element is there, that will be creating a magnetic field. Okay. So now because of that orbital motion of the electron, okay, there will be a magnetic field created. Apart from that also, electron, there is a classical way of thinking also. You can see the picture. Apart from the orbital motion, it has got, it's about its own axis, it has got a motion that is called spin motion. And if there is a motion of a charged particle, it will produce a magnetic field, as you can see there on the right hand side top pictures, that if the motion is depending on the direction in which the electron is rotating, actually 2 types of magnetisms are possible for the electron. If you just, so every electron is like a bar magnet. So depending on the current, depending on the direction in which electron is rotating, the spinning I should say, okay, if it is spinning like this, as you could see in the picture, okay, the line of forces are moving up. Okay, so that you may define this as up spin state of the electron. So that means because of the spinning of the electron, you are creating a magnetic field, and that is defining one magnetic state of the electron. We call it up spin state, which you are plus half is the magnetic moment, half h card actually. On the opposite is that if electron moves in the opposite sense, okay, earlier it was moving in this way. If it moves like this way, okay, if it moves like this way, if it is moving like this way, like this pen is moving, okay, like this way, then one type of magnetic, the magnetic net, magnetism lines of forces will be moving up, as you can see. Classical way of thinking it is. So this may be making, giving one magnetic state. We may call it up spin state. And if the electron moves in the opposite direction, okay, the clockwise direction like this, okay, like this. So that may be lines of forces may be just opposite, okay. So it will, so now you get another magnetic state of the electron. So that means the spinning motion of the electron, okay, it may be whether it spins like this or this, depending on that, the magnetic state can be different. So it can have move like this. This is one state. So it is moving like, if you look here, it is moving like this, like this, okay, like this, move like this. So that is one magnetic state, or move like this, that is the another magnetic state, okay. Two magnetic states are possible. There are the two spin state. If it is lines of forces are moving up, you may call that the up spin, or lines of forces are moving down, you may call it the down spin state. What I am trying to tell you with all these things, now because of the any current element is there, electron is moving. So charge particle moving means magnetic field will be there. So depending on the spin, particularly to the spin motion, the spinning in the orbit, okay, you can define two types of magnetic state. See, every electron is like a bar magnet because of this spinning motion you can think about. And that bar magnet can be of two types. Either, so electron can either move like this or move in the opposite direction. Either it can move in clockwise direction, or it can move in anti-clockwise. Electron can spin either in clockwise sense or in anti-clockwise sense. So it can have two types of spin state. One is a if we call one of them has got up spin state, the other one is down. So electron can produce two types of magnet. Okay. So the spinning state, therefore the magnetic state of the electron. Now if you think in the opposite way, every electron has got a charge. Now I am telling every electron is a small magnet. Now charge state you define by the charge of the electron. Now that every electron is a small magnet, that this is the magnetic state of the electron, and you define the magnetic state of the electron with a term called spin. Electron can have only one charge state. Electron is a negatively charged particle, and electron can have two spin states, two magnetic states. Okay, either either up spin state, that is magnetic moment half h cut, or down spin state, magnetic moment half minus half h cut. So spin of the electron is therefore a intrinsic property, the magnetic property of the electron. Okay, so it is a magnetic property of the electron, and so this spin is the key. So it may be the up spin or down spin. So up spin is one magnetic state, one quantum mechanical state. Down spin is another quantum mechanical state. We may call up spin as zero state. We may call one state as the down spin down state. You see, there is a beautiful comparison is there. Classically, up and down, you know, as because of the electronic motion. Now the mixtures, up may be one state, quantum mechanical state, down is another quantum mechanical state, but their mixed states are also allowed state. Okay, so spin is the key, it is a magnetic property of the electron. Okay, now that spin is representing the qubits in our case. So now let me again use pen and paper to show you something more. Okay, this to show you something more. Okay, some more ideas will come up now. They're good ideas, I should say. So just wait a bit. The up spin state, and that is the down spin state. So these up spin state we may call this zero state, and this down spin state we may call this as one state. So these are the two spin state of the system, up and down. Zeros and one are the two spin state of the system. Now what I am trying to do now, that if suppose electron is moving like this way, I am considering this as the up spin state of the electron or zero state, and electron is moving like in the opposite direction. Okay, and I am considering this as the down spin state of the electron, the other magnetic state. Now these are two qubits. Okay, 0 is a qubit, 1 is a qubit. These are the qubits. Now I need to generate mixed state. How? That is the question. How do you generate the mixed quantum mechanical state? So if you think in terms of that mixed state equal to psi equal to alpha 0 plus beta 1. So this 0 is the up spin, this 1 is the spin down state of the electron. So 0 means electron, okay, the other two spin state of the electron. 0 means electron is moving like maybe this way. 1 means electron may be moving like in the opposite way. So that means if I use the Bloch sphere representation, this may be the 0 state, and this the other one is the opposite state, 1 state. So if this is my representation, okay, so now I have to go beyond zeros and ones. Okay, I have to generate this mixed state, this psi 1, psi 2. I have to get this mixed state. How do you get it? Now, common sense is that if you look at the picture, that means you have to rotate this. Or if you have to bring here, you have to rotate this. You have to give rotation. So that means when you are going from zero state, 0 to 0 state or 1 state, when you are forming the mixed state, okay, forming the mixed state, according to my picture, say psi 1 is a mixed state, psi 2 is a mixed state. This may be another mixed state. I may call it psi 3. When you are forming this mixed state, so what you are doing, this mixed state, that is what you are creating here. How do you create it? How do you get it? That means you have to give a rotation to these zeros and ones. You know, rotation is an operation. You have to do operation of the initial 0 vector and 1 vector. So to get the mixed state. Okay, so now I am talking about what, if I try to keep it simply, if this is my Bloch sphere representation, let me take it better way. This is 0 state and this is the 1 state. Now these are the intermediate state. How do I achieve? Through rotation. Now what I am trying to tell you, in this rotation is an operation. Now because spin is a magnetic property, so that means in practice, two way of looking. How do I can rotate it? You apply an external magnetic field, same thing happens. Suppose in front of a bar magnet, I keep a needle magnet. So if you bring it in front, it will be rotated, maybe by some angle theta because of the torque, magnetic moment of the first bar magnet. So it will rotate. So the external magnetic field will try to rotate it in favor of the fields. So here also, if I have to rotate it, in practice, we need to apply field, external magnetic field. Now that magnetic field, you will interact with will operate on spin states of the electron or rotate the spin state of the electron. Okay, mathematically, so this is a practical one. Okay, we need to apply a magnetic field which will rotate the spin of the electron. Now, but in quantum mechanically, I have to tell you the mathematics part also. Mathematically speaking, what you are doing, there is a spin vector, zero vector or one vector, whatever you are saying. You are trying to rotate these vectors. You are trying to rotate it. You are trying to operate it. So there must be a corresponding mathematical operator for that. So we need to know the operator. There will be a correct operator which will be rotating zero vector or one vector. Now those operators are called Pauli operators. Okay. The operator that can rotate spin are the Pauli operators. Okay. The operators which can rotate spin Pauli spin operator. Now there are three types of Pauli spin operator. One of them is sigma x. Okay, this is 0, 0, 1, 1. Actually, corresponding matrix is Sx is equal to up h dot sigma x. It will act on the spin state. Sigma y. Some people call it sigma 1 also, whatever you like. This is sigma 2. This is 0 minus I0, Sy. And there are three Pauli matrices are there. Okay, the examination you will be asked to write down these. Many times it has come. Now the job of these three Pauli matrix is to act on the zeros and ones and rotate them and generate the various quantum mechanical states. So let us see how it does it. Okay, it is very funny. Suppose I have got this much. Suppose I have got, this is my quantum mechanical state. Suppose I have got an electron in zero state. So electron is there, it is in spin up state. Now this is my Bloch sphere representation. Okay. Let me do it in a better way. Okay. So this is your Bloch sphere representation. Okay. This is the spin up state. And you know this is the spin down state. What I am trying to do, I am operating Pauli matrices. Suppose I operate sigma x on 0. So now Pauli, now spin matrices are now being applied. If I apply, what is their job? Their job is to rotate 0 or 1. Now let me do it. If I operate sigma x on 0, sigma x is nothing but this much. 0, 0, 1, 1. Now this is nothing but you can understand 0, 1. So this becomes this much. Now you see you have done a beauty here. Sigma x 0 is acting, this 0 is this much. And you have produced this much. So what you have done a beauty there. Sigma x 0 You have made it 1. So you have done a beauty there because of this small operation. This is nothing but what you have done, you have converted these zeros into 1. So you have flipped it. This is the, okay, this is the not operation. Okay, quantum not operation you have done, Q not operation. So how Q not operation you are doing? Just simple thing. Okay, sigma x operating on 0, producing opposite is true. If sigma x was acting on 1, then it should be like this: 0, 1, 1, 0. You can understand it will be like this much. Okay, it will be multiplied like this. Now this is 0. So if you have got 1, it is getting into 0, and if you have got 0, it is getting into 1. So basically, it is now getting to 0. So what is actually happening? What is actually happening? Okay, pi rotation is taking place. Okay, pi degree of rotation is taking place. Okay, not okay. So quantum not operation means the rotating the vector by an angle phi by the help of external magnetic field. So I've introduced quantum not gate in front of you wonderfully, beautifully also. You can realize it. So now popular symbol, the quantum not operation is symbolized like this way. Obviously, you have to manipulate electron spin. You can realize. Okay, you have to realize, manipulate the spin of the electron. Suppose suppose iron atom. Few iron atoms are there, iron chain. Obviously, these are all nanoscopic system. So all of them may be with upspin state. So these are all spin zeros, zero state. Now you are doing not operation. Not gate is usually represented by symbol X. It is also called X gate, Pauli X gate. So what it will do? It will flip it. It will provide you all the down state. So this will become all 1. So this will be flipped. Spin will be flipped. This is called quantum not operation, and practically speaking, if this is your 0, this is actually rotated by an angle pi. That is what you can see there. So basically, it is doing the job of a rotation. Now a similar operation is there also, that is called, you see, so therefore this is very similar to classical not gate operation. Now very wonderful idea is that is called root not gate operation. Linear combination of these two. Any mixture of alpha and beta is satisfying this relationship. Okay. Any value, any combination. Only thing you have to choose the right value of alpha beta. Okay, and this is the representation, you know. Any point here is a qubit. Any point here is a qubit. Any point here is a qubit. Okay. Now the next point is that, so I can realize this 0 maybe as upspin state, spin up state of the electron, and the 1 as a spin down state of the electron. Okay. And what is spin, that we just came to know. So what we are trying to do now, We are trying to manipulate this electron spin, okay? The spin of electron. We are trying to manipulate this electron spin. That means, suppose this is my spin up state and this is my spin down state. Okay. Now my job is to produce this intermediate state. So if you consider upspin state, this is like a bar magnet. So these are your lines of forces are moving like this. And here the opposite story. It is down state. So what you have to do up in between, you have to create the magnetic state. Okay, these are intermediate size. This will be 0. This will be 1. But these size are important. Now the question is that how do you get it? How? Answer is that apply external magnetic field, because here I am talking about the magnetic property. Okay. Here I am talking about the magnetic property. So idea is that an external magnetic field, if I show it here, in presence of external magnetic field, suppose you are keeping a magnetic material, maybe a bar magnet, needle magnet. So what happened? These are the lines of forces. Now magnetic, okay. So what you are doing, suppose it was initially in this direction. Now you are actually rotating it by this angle theta. So in this way, how close this magnet is, okay, based on that actually, we could calculate this angular rotation. Okay. So what you are doing, if you think mathematically, you are actually manipulating the spin of electron. You are actually manipulating electron spin. Suppose this is the spin of the electron, okay, spin up, it is represented by zero state. It's because it's a state vector in two direction, two elements. So one may be 1, another may be 0. Now what we are trying to do, we are applying one external magnetic field. So if this is the direction, suppose this is your bar magnet. Okay. Now if I try to apply a strong magnetic field in this direction, now what magnetic field is doing? It is actually rotating the small magnets. If it was like this much, and if it is like this much, this is H external. That is the initial direction. So what it is doing, it is actually rotating it, maybe by some angle theta, or maybe like this, maybe some other angle, say phi. So now, if you do so, in presence of each external, the answer is that we can get the intermediate states. So from here on, any rotation by angle theta, how do I do the rotation? By external magnetic field. That is the message. So therefore, external magnetic field is playing the role of an operator. It is acting on the function psi and theta, or whatever it may be, and trying to rotate it. Okay. Now, according to Pauli, mathematically, there are is a rotation is an operation. According to Pauli, there are three types of rotation operators. This is the magnet, and you are trying to rotate it. And suppose it is rotated like this. Now, rotation means what you have done actually, you have done an operation. Now, according to this, it's an operation. There are three Pauli matrices, okay, who does all this operation. Three Pauli matrices are there who actually does all this operation. One of them is sigma x, this is sigma x, sigma y is basically this much, sigma z okay. What is their job? Their job is to act on the linear basis vectors. Expect what they will do, they will act on the electron spin and try to rotate it in favor of the field. Now what they does, what these are what these operators are doing actually. Let me give an example. If I give the example, you will realize it is so easy. So sigma x, as you can see here, zero zero one one. Suppose this sigma x is operating on the zero vector. Zero one one zero. Now if you look at the operation, sigma x 0, this is 0 1 1 0, this is 0 1. Now this quantity is the idea of what it is doing. It is doing the NOT operation. This is basically quantum NOT operation. Similarly, if you do the opposite, if you operate sigma x on 1, So what it does, it tries to know this value. So how do you know it? Suppose it is acting on the one state. Okay, so this is also Q not operation. So that is what I did here. Many more logic gates are there. Sigma, this is called sigma X gate. Okay, so Q not gate is the first quantum logic gate that I am sharing with you. This is like this sigma. How do you realize? Related circuitry is that you need a system suppose with all electron up spin. Hmm. Say maybe all are in zero. So now if I operate X gate, they will be switch over to this is the Q naught operation. Similarly, there may be sigma Z gate. It's like this. Sigma Z is very popular. A related circuit is like this. This is a circuit. If it is hmm, sigma Z gate is slightly different. Suppose you operate it on state. So if you multiply, this becomes like this much. So if you multiply this, you get this much. 1 into 1. So what it does actually, you see, now these operation actually phase shift gate operation. Actually, many more logic gates are there. We'll discuss it that in the next class. Okay.